In the next few videos, we're going to talk about how to construct LL1 parsing tables. And in this particular video, we're going to begin by looking at how we build something called first sets. Before we get into the main topic of this video, which is something called first sets, we need to say a little bit about how we're going to construct parsing tables, or what the conditions are for constructing LL1 parsing tables. And so what we're interested in knowing, we're building a parsing table, and we want to know for a given non-terminal A, okay, this is the leftmost non-terminal, and a given input symbol, the next input symbol T, we want to know under what conditions we will make the move A goes to alpha. We'll replace A, the non-terminal, by the right-hand side alpha. All right, and that means that the entry in the AT entry in the table would be alpha. And there are two situations in which we would like to do this. All right, so the first one is if alpha can derive T in the first position. That means that beginning with alpha, there is some derivation, some sequence of moves, could be 0 or more moves, that will result in a T appearing in the first position of the string that's derived. And if there is such a derivation, then using the move A goes to alpha at this point when T is the next input symbol would be a good idea, because then we would be able to match the T. Eventually alpha could generate the T, and then we'd be able to match the T and then continue with our parsing of the rest of the input. All right, so in this situation, when alpha can generate a T in the first position, we say that T is an element of the first of alpha. T is one of the things, there may be more things, but T is at least one of the things that alpha can produce in the very first position. One of the terminals, I should say, that alpha can produce in the very first position. Now, there's another situation, a slightly more complicated situation, in which we might want to make the move, or we would want to make the move, that if we see A as the leftmost non-terminal and T is the next input, that we'd like to replace A by A goes to alpha. All right, and the situation here that we're going to consider is, what if alpha cannot derive T? So alpha cannot, in any sequence of moves, derive T. So in fact, what does that mean? That means T is not going to be in the first of alpha. Okay, so, and our next input symbol is T. We're still looking at the situation where we have A as the leftmost non-terminal and T is the next input symbol. Now, this doesn't sound very promising, because we have an input symbol T that we want to match, and the leftmost non-terminal that we've got up next, that we have to do a derivation for, can't generate the T. And so, but it turns out that that it's not hopeless, that we actually may still be able to parse the string even in that situation, provided that alpha can go to epsilon. So if alpha can derive epsilon, if alpha can go away completely and we can basically erase the alpha, then it could be that some other part of the grammar can come in and match the T. All right, and so in what situation would that be? Well, here are the conditions. So if A goes to alpha is a production, and alpha can go to epsilon via 0 or more moves, all right, so alpha can eventually be completely wiped out, all right, and if T can come immediately after A in the grammar, so there has to be a derivation for this to make sense. There should be a derivation where we are using the A, okay, where the A is an important piece of the derivation, from the start symbol. And what comes immediately after the A is the next input symbol that we're expecting. So in this situation, if we could get rid of the A, then by having it go to epsilon, then we would still be on track, because potentially some other piece of the grammar could come in and match the T. All right? So in that case, we would say, what do we have to test for? Under what conditions can we do it? Well, we want to be able to do this if T can come after A in the grammar, and we say that T is in the follow of A. T is one of the things that can come after A in the grammar. Now, this is an important point and a place where people sometimes get confused, and so I want to emphasize this. Notice that we're not talking about A deriving T. Okay, A does not produce T. T appears in a derivation after A. Okay, so the A and the T here, it doesn't have anything to do with what A produces. This has to do with where A can appear in derivations. All right, so if the T can come after the A in a derivation, then we say that T is in the follow of A. All right, so in this video, we're going to focus on only this first part, the first sets. In the next video, we'll look at the follow sets. And then in the video after that, we'll talk about how to put it all together to build this parsing table. All right, let's focus now on our main topic for this video, the computation of first sets. So here, first of all, we have to have a definition of what a first set is. And so we're going to say for an arbitrary string, this is actually, X here is a string, it could be a single terminal, it could be a single non-terminal, or it could be a string of grammar symbols. All right, and if that X can derive T in the first position through some sequence of moves, then we say that T is a terminal here, is in the first of X. Okay, so all the possible terminals that can be derived in the first position will be in the first of X. Now, for technical reasons that will become clear in a minute, we also need to keep track of whether X can produce epsilon. All right, so even though epsilon is not a terminal symbol, if X can go to epsilon via 0 or more steps, then we'll say that epsilon is in the first of X. And this turns out to be needed. We need to keep track of whether whether things can produce epsilon in order to compute all the terminals that are in the first set of a given grammar symbol. All right, so now here's a sketch of the algorithm. So first of all, for any terminal symbol, well, the only thing the terminals can produce are themselves. So every terminal symbol, and here I should just say T is a terminal. So for every terminal symbol, it is in its first set just consists of the set containing only that terminal. All right, so now let's consider a non-terminal X. Okay, so here X is a non-terminal. And what can be the conditions when epsilon is in the first of X? Well, if there's a epsilon production, if X goes immediately to epsilon, then obviously X can produce epsilon, and epsilon should be in the first of X. But also, if X can produce any other right-hand side, all right, where everything on the right-hand side can go to epsilon, well, then the whole right-hand side can go to epsilon. So in that case, also, epsilon is in the first of X. And notice that this will only happen if it can only potentially happen if all of the AIs here are non-terminal symbols themselves. Obviously, if there's any terminal symbol on the right-hand side, then that production can never go completely to the empty string. Okay, it'll always produce at least that terminal. But if every non-terminal on the right-hand side can produce epsilon, meaning epsilon is in the first of all of those non-terminals, and there are no terminals on the right-hand side, then epsilon will be in the first of X. All right, and there's one other situation, and here's where we make use of the fact that we're keeping track of where epsilon can be produced. All right, so let's say that we have a production like this, okay, and let's say the first n symbols, A1 through AN here, can all go to epsilon. So this can all disappear, okay, and be replaced by the empty string. Well, what does that mean? So if we have a derivation like this, okay, and then through some number of moves, it goes to alpha, well, that means that X can, through a bunch of moves here, derive alpha itself. Okay, so X can go to alpha by wiping out all of the AIs, and I forgot to put the alpha here on the end. There should be an alpha after A sub n there. Okay, and what does this mean? Well, this means that anything that is in the first of alpha is going to also be in the first of X. All right, so if any prefix of the right-hand side can disappear, then the remaining suffix, the alpha, it doesn't matter what the alpha is left. Then the first of alpha will be a subset of the non-terminal on the left-hand side, X in this case. All right? Okay. All right, so that is a definition of first sets and how you compute them. Okay, and we have to compute them for the terminals and for the non-terminals. All right, that's what these second two rules here cover, the non-terminals. And just notice, as I mentioned here at the beginning, that this is well defined for any other grammar sequence as well. I mean, excuse me, any other string in the grammar as well. If I know how to compute it for terminals and I know how to compute it for non-terminals, then I can compute it for arbitrary strings in the grammar as well. All right, so now let's do an example. Let's take a look at this grammar, and let's see if we can compute the first set. So let's start with the easy stuff. Let's do the terminal symbols. All right, so For the terminals, it's really extremely straightforward. The first of plus is plus. The first of times is just times. Every terminal has its first set. The first set of every terminal is just the set containing that terminal, and so on for the others. And this is not worth writing out. So it'll be the first of open paren will be just open paren. The first of closed paren will be just closed paren. And I think that is all. No, we have to do int as well. Okay. All right. So these are the first sets for the terminal symbols. And now let's look at something more interesting. Let's talk about the first of the non-terminal symbols. So what about the first of E? Well, if we look at the production for E, let's remember our rules. So we know that anything that's in the first of T will also be in the first of E. So the first of T is a subset of the first of E. Okay, so in order to know what the first of E is, we have to know what the first of T is. At least to know part of the first of E, we have to know the first of T. So let's move on then to first computing the first of T. Let's try to get that set. Now, the first of T is actually pretty easy because if we look at the productions for T, we can see that they produce terminals in the first position. All right, so the only possibility only possibilities in the first of T are open paren and int. And since there are only two productions for T and both of them have a terminal in the very first position, there's no other terminal symbols that could be produced in the first position by T. So we can just read off the first of T directly from the grammar. And it's the open paren and int. Okay? Now, let's return to thinking about the first of E. So remember there was another case that we have to keep track of, or that we have to consider. So it could be, so clearly everything in the first of T is in the first of E, all right? And we've already noted that down. But if T can go to epsilon, then things that are in the first of X could also be in the first of E. But now we've computed the first of T, and we see that epsilon is not in there. The first of T always generates at least one terminal symbol. And so there will never be a situation in which X can contribute to the first of E because T is always guaranteed to generate at least one terminal. So in fact, this subset that we wrote up here is not a subset at all, it's an equality. The first of T and the first of E are equal. So the first of E is also open paren and int. All right, so now let's take a look at the first of X. Okay, so the first of X, well, clearly plus is in the first of X because one production for X produces a plus immediately in the first position. So we can just add plus to the first of X. And then X has an epsilon production. So it can also go to epsilon, so that means that epsilon is also in the first of X. And now what about the first of Y? Well, the first of Y, it's a similar structure to the productions for plus. We see we have one production here that produces a terminal in the first position, and that's times. So the first of Y has times in it. And then Y also has an epsilon production. Y can go directly to epsilon, so epsilon is also in the first of Y. All right? And that's actually it for this grammar. These are the complete first sets for all the symbols of the grammar. The terminals just have themselves in their first sets, and then the non-terminals we computed have these sets. So that concludes our discussion of first sets, and in the next video we're going to take a look at computing follow sets.